Hello, so welcome to this video on exoplanets. I apologise if the quality at times on the audible isn't perfectly, great. With December, lots of colds are going around. However, one very fortunate thing is that, as much as certain bacteria and viruses might be thriving, human life is also flourishing on this planet. However, if we look ahead about 5 billion years, the sun is going to swallow the earth, which will put, a bit of a damping on the human race unless we find somewhere else to survive. And this is one of the many reasons why science is fascinated at the moment with the idea of exoplanets, so planets outside of the solar system, and whether they may be habitable. And in this video, I wanted to explore with you a neat little bit of math you can do to work out the various possible sizes for exoplanets that might be able to support human life. Now, human life involves so many factors that to do that rigorously would take a lifetime, and it's not healthy to spend a day, let alone a lifetime, watching a YouTube video. So I am just going to look at a few things, but we'll see by just considering what kind of gases the planet would have to hold on to, which gases it would have to release in the atmosphere, and what kind of structure we want the planet to have. So whether we want it to be a water-to-world, a gas giant, or a rocky planet, we can come to predicting a maximum value for a habitable exoplanet and a minimum value for the size of a habitable exoplanet. So that's what we'll be doing in this video. There'll be a little bit of maths, not much. The main thing is using all the physical ideas behind the maths. So to start off with, we're going to look at the atmosphere of a planet that might harbour life, and that will take up most of this video, because by considering the atmosphere, we'll be able to find maximum and minimum values for the ratio of the mass of our habitable exoplanet to its radius. Bring us closer to finding maximum and minimum values of the radius itself. But to get to the ratio for mass to radius of the planet, and to link that with the atmosphere, we're going to do it through considering if we have a planet of a particular mass and a particular radius, what kind of gases can the planet capture and which can't it capture. And that's based around whether the molecules in the atmosphere are moving fast enough to escape the planet's surface or not, or the region around the planet as well. So we need an equation that will give us, the speed of the molecules at a particular temperature, or their energy. And the equation that does this is one that tells us that for every degree of freedom, a molecule of a substance on average will have about half times kBt worth of energy. Now, Kb is Boltzmann's constant. It's one of the constants for our universe. T is the temperature of the gas, or in our case, the atmosphere of our exoplanet. Now, we don't really care exactly that we have a factor of a half, because there are so many approximations going into this video. However, it's a good place to begin, and to turn this into the amount of kinetic energy a molecule of a particular gas would have at a given temperature, we need to consider how many degrees of freedom a molecule would have. Now, a degree of freedom is kind of a independent quantity that allows us to predict the future state of that molecule. And if we're thinking of predicting future state in terms of the position or velocity of the molecule, as you do in a certain kind of classical physics called Hamilton's mechanics, then we need to think how many distinct positions, well, spatial axes are there in space, or how many distinct components of velocity could our molecule have? Well, we have three spatial dimensions, so if we ignore degrees of freedom relating to things like atoms rotating about molecular bonds and all of that complexity, we have that the energy, the kinetic energy of a molecule is about 3/2 kBt, because there are three, independent degrees of freedom, given we have three spatial dimensions in our universe. Now, we're going to want to relate this energy to the energy of a hypothetical molecule which at a given temperature has just enough energy to escape the planet. When our molecule has just enough energy to escape the planet, we say it's moving at the escape velocity. Now, if the energy of our molecule is less than a half mv escape squared, where v escape is our escape velocity, then our molecule doesn't have enough energy to move at or above the escape velocity, so it's moving too slowly to be able to escape the planet, and so will become part of the planet's atmosphere. And I'll call the energy a molecule would have where it's just enough speed to escape the planet. So when it's moving at the escape velocity, I'll call this energy the kind of critical energy, and I'll call the mass of a molecule that has the critical energy at temperature T, I'll call the mass of that molecule M. And you can relate the temperature to the mass of a molecule which is moving at the escape velocity to the escape velocity by relating your equation for critical energy to your equation for the thermal energy. Because the thermal energy of a molecule is its kinetic energy, because when we say thermal energy, we really mean randomized kinetic energy of the molecules. Now, this is a useful equation, but at the moment it's relating the temperature of our atmosphere to the mass of a molecule which is moving at the escape velocity to the escape velocity. So we've got temperature, which is good. We've got something about the mass of molecules, which might help us go from here, because we need to consider what kind of molecules our planet will and won't trap. But at the moment we're relating it to escape velocity from the planet's surface. We want it to relate it to the radius of the planet, and that is what we'll be doing in the next bit of the video. So we've done pretty well so far. We're getting towards a range of values for the radius of our exoplanet. So our upper and lower bound on the value of capital R for the planet, we might one day travel to and survive once our sun swallows the Earth, but we're not quite there yet. And one of the reasons we're not quite there yet is we haven't got an equation with capital R in. However, we do have an equation that is relating the temperature of the atmosphere and the mass of molecules within the atmosphere to the escape velocity. Unfortunately for us, the escape velocity can be written in terms of the mass of the planet, so capital M, and the radius of the planet, so capital R. So here's our equation for escape velocity. If you would like to know a bit more about escape velocity, I've kind of got a video on it where I talk about finding the size and also density of black holes, which are objects where the escape velocity kind of around a region is the speed of light. But yeah, we're not worried about black holes for this video. For us, the beautiful thing with the escape velocity now is that it kind of contains the mass of our planet and the radius of the planet. So we have our kind of equation, and it's always worth checking that our equation makes kind of logical sense. I mean, we can see from our equation, the larger the mass of our planet, the higher the escape velocity. That makes sense because very heavy objects like the sun, or if we pick a gas giant like Jupiter, they have a very strong gravitational pull, so we would expect a high escape velocity. But also, if you have mass compacted in a really small region, that also generates a high escape velocity. An example is neutron stars. Despite them being really small, I mean, so small they're kind of not even astronomical. Like they're big relative to a human, but they're really twitchy in size. But they have a huge mass contained within that, giving them a really high gravitational pull. And black holes is another case where the stellar mass black holes are not typically very big, but the escape velocity from them is so huge because the matter is so concentrated for the black hole to have formed. So we have an equation that does make sense, and if we now put it into our equation that is linking the temperature of the gas, the mass of molecules in the gas, to the escape velocity, we end up with our bottom equation here. And now if we just do a bit of rearranging, we end up with our bottom equation in blue, where I pulled out the kind of like factors, if you like, and we can see from this equation that the ratio of the mass of our exoplanet to its radius is proportional to 1 divided by the mass of a molecule that has just the right mass to have a speed equal to the escape velocity, and therefore can just about escape the planet's atmosphere. And if we want to calculate the value for the constant of proportionality, so the terms outside of our brackets, well, Boltzmann's constant is just a universal constant, so we can use that. The temperature of the atmosphere is something we can, estimate from, temperatures that we're comfortable with on Earth, because we're trying to find the radius of an exoplanet that humans can survive on, or a range of radiuses an exoplanet could have. And it's no good having a exoplanet of the right radius if the atmosphere's temperature is so cataclysmically wrong that after a few days there, humanity would become extinct. So we need a suitable temperature. So let's take the temperature to be about room temperature, so about 300 Kelvin. Now I am making a fair bit of a simplification here, because evidently whilst we would like a suitable temperature close to the planet's surface, it doesn't really to us matter that much what the temperature of the atmosphere is, that's say a few kilometers from the planet's surface. Because we don't fly, it doesn't really matter to us. So the actual average temperature of the atmosphere, averaged out over the temperature at different heights, might be a little bit below 300 Kelvin, but I'm going to take it to be about 300 Kelvin. So about room temperature is a good approximation, and if we put those into our constant of proportionality, and also remember that G is the universal gravitational constant, so that's about size of about 6.67 times 10 to the minus 11, we end up with saying that our constant of proportionality is 9.31 times 10 to the minus 11, and so the ratio of the mass of our exoplanet to its radius has to be 9.31 times 10 to the minus 11 divided by the mass of a molecule that would have a velocity equal to the escape velocity, and therefore just about be able to escape the planet's atmosphere. Now, if we want to get values for ranges of our ratio, so a maximum and minimum value for capital M over capital R, we need to have some way of having a maximum and minimum value for small m, but we can get that by considering what kind of gases we would like our planet to hold on to. So we can do things like breathe, or at least breathe in the necessary type of chemicals to respire, and therefore for ourselves to survive. But also consider what kind of gases we do not want the planet to capture. So what kind of gases might be harmful in the atmosphere or potentially very dangerous. And that will give us an upper and lower bound for small m, which will allow us to find an upper and lower bound for capital M over capital R, bringing us closer to finding, the range of radiuses our exoplanet might have. So if we're going to find upper and lower bounds for our ratio, and I'll call our ratio K, so that's the ratio of the mass of the planet to the radius of the planet, we need to find upper and lower bounds for small m. And to do that, we have to consider, if a molecule had a mass bigger than small m, would it escape or would it not escape? And similarly, what would happen to molecules with a mass, the other side of small m. So if we think about all the kind of molecules within our atmosphere, if we consider each molecule having the average kinetic energy of molecules at that temperature of that particular substance, so we are simplifying a bit there, we're assuming all molecules have the same energy. But it's a good kind of approximation, because we saw that the average energy of a molecule of a particular substance will depend on the mass of the molecule. Sorry, it will depend on the temperature of the molecule, but the average kinetic energy will not depend on the mass of the molecule. So all of our molecules within our atmosphere will have the same kinetic energy, because we're approximating our atmosphere to be at a uniform temperature, and each molecule has 3 distinct axes it can move around, so we have 3 degrees of freedom. So all the molecules have the same energy, is our approximation. In truth, it's all the molecules have the same average energy, where we're averaging out over different molecules within a substance, but that's getting a little bit too detailed for what we need to do. So we're saying all molecules have the same kinetic energy. Well, if we have a molecule that has larger mass than another molecule but has the same energy, then our molecule with larger mass must have a smaller velocity, and that allows the kinetic energy of our 2 molecules to be the same. So if we've got a molecule with a mass bigger than small m, it must be moving slower than our escape velocity, and so our planet will hold on to substances made of that molecule. So if we've got a substance where the molecules have a mass bigger than m, then those are the kind of substances our atmosphere will be made up of. Whereas if we have a substance with molecules with a mass which is smaller than small m, then they're going to be moving quicker than the escape velocity, and therefore will not be held by the planet's gravity. And so if we will find upper and lower bounds for m, we can use that idea. For example, let's think about molecules that we do not want our planet to keep hold of. So molecules that will give us a lower bound, if you like, for small m. Well, we don't want our planet to keep hold of substances like hydrogen. And that's because hydrogen is incredibly flammable. If you've done the chemical test for hydrogen, you'll know that one way to test hydrogen is to put it in a small container, and then put a flame near the hydrogen. And then the combustion is so strong when the hydrogen is reacting with oxygen under heat that there's a squeaky pop, which essentially almost pops out the flame, and it's quite a squeaky, fairly loud sound. So the explosion is so energetic that significantly energetic sound waves or pressure waves are created in the surrounding air. So hydrogen is incredibly flammable. So we do not want our planet to hold hydrogen. So whatever our value for small m is, i.e., the value for the mass of molecules which have an escape velocity, which have a velocity equal to the escape velocity, small m must be bigger than the mass of a hydrogen molecule. Because these hydrogen molecules must be moving faster than the escape velocity of the planet, so that hydrogen can escape away into outer space. However, we do want our planet to keep hold of oxygen, because we need oxygen to react with glucose so we can respire and therefore produce energy. We do have methods of anaerobic respiration that do not involve oxygen. However, we can really only use these in reserve. They're not very reliable we definitely can't use them in the long term because anaerobic respiration produces lots of waste products like lactic acid, which we need oxygen to actually break down or to turn something safe. I mean, lactic acid is a thing that causes muscle cramps. It's not something you want building up in your body, so we need oxygen. And so putting that together, we have a lower limit for small m, and that lower limit is the mass of a hydrogen molecule, and we also have an upper limit for small m, and that is the mass of an oxygen molecule. So what are the masses of these molecules in kilograms? And we want to use it in kilograms because we can then substitute our lower and upper bound for small m to get a lower and upper bound for k, which is where we're going with this. So if we look at hydrogen as a molecule of hydrogen is a diatomic molecule, so it's got two hydrogen atoms. Each hydrogen atom has kind of one nucleon, so one particle in the nucleus, and it's really the nucleus which is making up the mass of our atoms or our molecules. So the mass of hydrogen is, to an extremely good approximation, the mass of two nucleons. And a nucleon, I'm taking it to be the mass of a proton. I mean, even though neutrons have a slightly different mass, they have very, very similar masses, neutrons and protons. So it doesn't really matter which one we pick. But if we pick a proton, we get the mass of a hydrogen nucleus is about 2 times the mass of a proton. Sorry, the mass of a hydrogen molecule is about 2 times the mass of a hydrogen proton, which is about 3.34 times 10 to the minus 27 kilograms. And doing similarly with oxygen, Well, each oxygen atom has 16 nucleons. You can get that from looking up the atomic mass of oxygen in the periodic table. But an oxygen molecule is 2 oxygen atoms, so we have 32 nucleons within the molecule, giving us a mass of 5.34 times 10 to the minus 26 kilograms. And so we now have a lower and upper bound for small m. And we can put those bounds into our equation for k, giving us a lower and upper bound for k. So we've now got a upper bound for the ratio of the mass to the radius of the planet and a lower bound for that ratio. But we want to get towards kind of lower and upper bound for the radius itself. So we want to look at something else that is going to have mass and radius in it to give us a new piece of refreshing information. Well, we've looked at the atmosphere, we've looked above, so let's look below, let's look to the ground and see what information we can get out of the ground or the density of our exoplanet if it's going to support human life, and putting that information with our upper and lower bounds for k, we will be able to find ranges for the size or the radius of a exoplanet that could support human life. So if we look at kind of the Earth is kind of a rocky planet and it's about spherical, and most planets, unless they're spinning really, really quickly, are approximately spherical. And if they're spinning so quickly they're not approximately spherical, that in itself will create huge issues, because then you'll have difficulty with the typical wind speeds if the planet is moving so quickly that the centrifugal forces are causing the planet not to be nearly spherical. So we're going to assume our exoplanet is spherical, meaning the mass of our planet is equal to the volume of a planet, where that volume is also the volume of a sphere with radius capital R, and then we've got to multiply it by the density to get the mass. And we called our ratio of m over rk, and if we look at our equation that links mass with density, we can see that k would have to equal 4/3 pi times r squared times rho, where rho is the density of the planet. And if we rearrange for k, we end up with this expression. And the beautiful thing with this expression is now we've got an upper and lower bound for k, we can find an upper and lower bound for r if we fix what rho, the density of our planet, should be. Well, let's record our upper and lower bounds for k first. So these were our upper and lower bounds. And if we're considering what a rho is, we remember that we want our planet, our exoplanet, to be a rocky planet if it's going to support human life. Because we're not water creatures, and for anyone who has done washing up for a little bit, you'll realise that your hands do feel a little different and your skin feels a little different if it's submerged in water continuously for even just an hour. So our skin would encounter huge issues if we were trying to survive in water for our entire lives, so for decades, hopefully. So we don't really want to live on a water-based planet. We want to live on a rocky planet. That's what our bodies are used to. That's what we're really evolved on. So what would a good density be? Well, let's take the density of Earth, a rocky planet, which is about 5,515 kilograms per meter cubed. And now if we use that density and our upper and lower bounds for K, then we can find a maximum and minimum value for R, and we get a maximum value of about 2.7 times 10 to the 5 meters, and a minimum value of about 1.1 times 10 to the 6 meters. And so putting that together, we have a range of possible radiuses for our exoplanet, which lie, to within, order of magnitude, something like, the size of the Earth. That's at the upper end of our kind of range of our, to, 10th of the radius of the Earth. And so we've got to ranges of, radiuses for exoplanets that might support life, really by considering a few assumptions together based on the composition of the surface and the density of the planet, and also the composition of the atmosphere. So what molecules we would like the atmosphere to have and what ones we would not like it to have. And the benefit of doing this kind of video is it shows how we can use fairly familiar physics to derive some pretty cool things that might be helpful for humanity moving forwards, and some quite cool calculations. And it shows that you don't have to, immediately go into, all the crazy stuff about, things like quantum field theory to do some really cool things in physics. And, I hope, given this channel does do a mix of physics, I hope it's also, helpful having some of these videos where we take more familiar equations and play with them a bit, because physics is all about playing, and you don't have to jump to all the weird and wacky stuff to have fun with physics. Having said that, if you love all the weird and wacky stuff with quantum mechanics and relativity, plenty of videos on this channel to check out. Recently did one on spin and polarization of light, and there's quite a few videos on quantum mechanics. But I try to keep this channel as mixed as possible to show how eclectic and broad physics can truly be. And if you're interested in astrobiology, so the study of possibility of life on other planets, there are loads of wonderful books out there. I mean, it's a really growing field. We're constantly finding new things about how life develops on Earth, and also finding new things about how planets form, where they can form, how long they can take to form. And so both from the astro and bio point of view, we're finding new information, feeding a really evolving discipline in physics, which might go to some really cool and interesting places. So I hope you enjoyed this video. Hope you got something out of it. And I hope to see you for some more wonderful physics soon.